Alright, discrete time. So far, we've been doing the continuous time because it's more like how our brains work in continuous time. We think that our brains work in continuous time, but actually our brain is also a computer. And it works in discrete time. But it's a very, very high-speed computer, so we don't even detect the discrete details of our brain. For example, if you can see my eyes, for example, you can follow my eyeballs. If I want to scan the room from one side to the other, follow my eyes if you can see. I start from here and I go across the thing, and what you notice is that I go boom, boom, boom, boom, boom like that. That's discrete, right? From one position to the other, to the other, to the other. But if I follow a reference, for example the pen, then my eyeballs are going to move in a perfectly continuous manner. Alright? You don't distinguish the jumps. So that's because the control system in the brain, feedback control, where the position of this and where my eye is, so that there is a change and my eye can follow this change in very small time intervals. Okay, so if you're in a disco, for example, and there's a strobe light in the disco and people are dancing, you see them like these robots. You miss the intermediate positions. But if you increase the frequency of the strobe, then you can see almost all motions continuously, just like the eye can follow the reference. Does that make sense? So, when you have a function in continuous time, okay, you have the time scale here and the position is here. Right? So the system is changing its position as time moves on. You are recording every single point on this line. But if you're switching to discrete time, then you're only recording the position of the system at given intervals. So at this point, when t is equal to 0, you recorded this, x to 0. And then your computer records this and stores this value for the rest of the interval period. Let's call that this is t, and we're going to call it sampling period. Until the next sampling period, which is going to be this is 0 TS, this is 1 TS, this is 2 TS, the intervals are equal, assuming 3 TS, and so on, all the way to n TS, okay, and going to infinity. Then the computer is going to record this and stay here. For the next period, you're going to have this value. Only at this time you sample the curve, so you get this value. So now for that, the next interval, computer remains here. It does not record these values, so there is an error in your recording. All the error being this much here, that much here, that much here, that much here, that much here. So therefore you're talking about the area of this almost triangle, right? So that's the integral, of course. Area is the integral of x dt. Right? That integral from ts to ts plus 1. Ts and ts to n plus 1 ts. Does that make sense? If ts is here n, then this is your value. The next value is going to be here. So your area of error is going to be this. So that's going to be n, and this is going to be n plus 1 ts. So this, your area of error is going to be the integral of the function between n and n1. Make sense? Okay. The way, so now you understand that the t variable, the independent variable, has changed to nts. Right? I'm not recording time anymore in infinitely spaced intervals, but I am recording n times ts, the value of x at n times ts times. Okay? And ts being constant, so I might as well say that I'm recording t, instead of t, I'm using k, because ts is constant. I don't have to repeat it every single time. So from a continuous variable, I have moved into a discrete variable. Alright, and I call this discrete variable the index. And the way I show my function now is here, and then here, and then maybe here, and then maybe here, and then maybe there, and then maybe here, so on. Right? I'm recording it at values of k equal to 1, 2, all the way up to n. Okay, so my variable, my index has changed from a continuous t to the integer n. Alright, so that's an integer index. We don't have 2.5 now. We don't have 2.8, 5, 6, 7, below. Okay? So it's an integer increments of sampling. And each increase in t from 3 to 4, for example, is an increment of the index. And as we said, the interval is always the same, the sampling interval. Okay? So, and I'm incurring continuously an error. The way to reduce this error is to sample this continuous function at shorter intervals. So instead of incurring an error of that much, I'm only incurring an error of this much. Okay, in the total evaluation of the continuous function in the discretization process. Discretization. Process. So then, every time I'm working with a computer, recording data and analyzing data, I am making an analog. This is analog. Analog means same knowledge as the function itself. Analog input to a discrete input. In other words, a digital input. Because I'm making this discretization process using a digital device, alright, which is composed of ones and zeros, only binary values. So it's digital. So we are making actually an A to B conversion. So when I measure the flow, let's say, of a pump, or measure the output of a power source, voltage source, okay? What I'm doing is the sensor value, the sensor is analog, this data, and then I put it into an A to B converter, okay? And I process the thing here, so I have a digital output here, and then I have a D to A converter to turn it back into analog. Okay, so most measuring and analysis devices that we're going to see in the next year, signal processing class, you're going to learn A to D, ADCs and DACs, the converters. Okay, you're going to try to, one, minimize the error in the digitalization or discretization process, and two, having the digital device analyze that discrete value. Okay, do the analysis, the processing, the signal processing in the digital device. Get a digital output and then convert it to analog again so that we can put it into a sync, which could be the oscillator, the screen of the monitor, and everything. Sync means where the water flows, right? So where the data flows, so that you can observe the data. Is that clear? Alright, so there is a sensor here, converter, processor, sensor, converter, and then the sync. That's what you're going to be dealing with all your lives if you're into research, electronics, or measurement, instrumentation, stuff like that, which is what you're going to be doing. So we need to learn how to manipulate not only discrete signals, okay, but also discrete systems, processes, discrete processes. So, let us go into this as I reduce T of S all the way down to positive, zero, which is not possible. Alright? The limit T of S goes to zero, at the limit, then digital turns into analog. Okay, that's what it is. If you could have a digital instrument with zero sampling period, then you would have directly an analog result. But as you know, frequency is 1 over t. So the sampling frequency is going to be equal to 1 over ts. And if the sampling period goes to 0, then the sampling frequency has to be infinite. And infinite frequency corresponds to infinite energy. And there is no such device. You can increase your sampling frequency to 10 to the minus 10s or 15s maybe. But that needs a very high-powered central processing unit. Okay? And most laboratories cannot afford it. So what you have to do is you have to be satisfied with, for example, 10 to the minus 5 central times, which means that every second you're taking 1 over 10 to the minus 5, which is equal to 10 to the 5 points of that. Okay? So if the TS is 1 second, okay, then you are taking the data every 1 second. Your sampling period is 1. Your sampling frequency is also 1. Okay? But as your sampling period decreases, your sampling frequency increases, and you start taking more and more samples every second. Okay? So you're almost there at the analog scale of the text, at least what you can perceive with your eyes. For example, when you do a MATLAB run, okay, and you look at a first order circuit response, you see this, almost analog. But if you amplify, zoom, zoom, zoom, zoom, zoom, you're going to see that this actually is something like this. If you have done this, you know what I'm talking about. Alright? Here, the scale of time is maybe 1 second and 2 seconds and 3 seconds here. But here the scale is 10 to the minus 5 seconds. Alright? 10,000 milliseconds. 100 milliseconds. Yeah, 100 milliseconds. And my 2 and 3. Whatever. Alright, it's too late for calculation. So I hope you understand what I'm talking about. I hope I can explain what I'm trying to say. So the bottom line is we have to understand discrete systems and discrete numbers. So again, referring to the continuous system, we have an input, U or T. It could be a response, it could be a step, it could be a and whatever. And the system, G of T. And then the output, let's say Y. This output is given to us by U of T, combined with G of T. Right? You know the convolution operation. Have you been taught the convolution thing? Not in math? Not yet? Okay. We will talk about that. This is a little bit, tricky operation. Students usually don't like it, but it's actually extremely simple. And when you move to the Laplace domain, then you have U of S, the Laplace transform of this, going into the G of S, the system transfer function. Okay, this is the Laplace transform of the signal input. This is the Laplace transform of the system. And this is the Laplace transform of the output. Okay? And then this becomes U of S times G of S. So one thing good about Laplace transform, other than you have to deal with complex numbers, is that convolution turns into multiplication. Convolution is an integral. So that is calculus. Integration, differentiation, all those are calculus operations. Alright? But multiplication is algebra. So the good thing about Laplace transform is that it turns integrals, it turns calculus into algebra, simple multiplications and divisions. Alright? It gives you a huge advantage in calculating the responses. The only problem is that since you came here through the transform, then you have to go back to understand what the output of this is the time domain. This is the time domain. And this is the Laplace domain. Right. These are the underlying foundations of ideas that we need to have in order to comprehend what's going on with the discrete systems. Not yet, all right? These are all continuous systems. Signals and systems. As we said, when we go into the discrete form, then we move from time to the index. Right? And we also move from parentheses to brackets. Okay? That's how we show that the signal or the system is discrete. And we use brackets. That's a convention. Everybody uses it. Some people don't, but it's helpful, advantageous to use the discrete brackets to indicate that what we're dealing with is the discrete system. So when we are in the time domain and we want to know the output of the system, we have to convolve the input with the output of the system. In Laplace domain, we just have to multiply, okay? Instead of going to the input. That's one. So we have to know what convolution is, both in the continuous systems and in the discrete systems. And also, in a discrete system, to facilitate, to make it easier to do this convolution thing, okay? We have to do in the discrete system both the convolution operation. In which case, this integral, particular integral, turns into a summation. Okay? The integral here is from 0 to infinity, and the summation time equals 0 to infinity, and here n is equal to 0 to infinity. Okay? So, in the A to B analog to discrete transformation, A to B, we switch from integral to summation, one thing. Okay? And when we do the U Laplace transform, we switch from S to C to the complex variable C. G of C and Y of C. Okay? And that also going to be a multiplication. U of C times G of C. Give us Y of C. Okay, so from analog to digital, we switch from S to C. From time domain to complex domain, okay, we switch from S to Z. Z is a discrete variable, and S is a continuous variable. G of C, U of C, and everything, interestingly, they turn into continuous functions. Even though the thing itself is discrete, we turn them into continuous variables. All of that is going to make sense in a few hours today. If they still don't, then I failed. as a teacher. So what we're going to do today is look into the convolution operation first. And then we're going to go into the discrete functions. Last week, we had learned how to define, how to represent systems, continuous time systems, in 6 different forms. Right? The differential equation, of course, balance, and then the governing equation, the differential equation, and the block diagram, and this and that. Now we're going to learn all of these in discrete form. Okay? This is the Laplace transform, as we said, and that is the transform. We're going to find, yes. What? Can I? It's a transform, like C, like this. It's a complex variable. Instead of expressing everything in time, we're going to express it in Z. So, yes. Z itself is continuous, but the Z transform is continuous, but what it represents is discrete systems. Okay? Confusing, but it won't be in our words. Okay, so in order to understand the convolution theorem, we have to first remember that what we are convolving here, systems, with the signal, is a linear time invariant system. Okay? Convolution doesn't apply to anything that's nonlinear and anything that varies with time. Okay, it has to be linear and time invariant. Now, linear, as you remember, has 2 distinct properties. One is superposition, and 2 is scalability. Time invariance means if I give the system an input today, I get Y. If I give the same signal tomorrow to the same system, I also get Y. So its output doesn't change with time. Okay? It remains invariant. It doesn't vary with time. Okay, that's time invariant. So if the system is linear and time invariant, then we can apply everything that I'm going to talk about today. But there are no such systems in nature. Everything is non-linear, and everything varies with time. So what are we doing here? Approximations. Okay? We are neglecting some effects. But by doing that, we are making our life easier, mathematical operations easier. But at the end, we know that we're going to suffer some consequences. We're going to have errors in our findings. Okay? But if we can use the engineering safety factor, we can get away with those errors. Alright? We talked about safety factors. So, when we talk about time invariance, what I'm talking about is time shift, which we saw last week. For example, delta function of t is given as 1 when t is 0, and 0 when t is not 0. And yes.
10 minutes left.
What?
10 minutes left.
No way. We just started. What are you talking about? What are you on Jupiter time? Yes, you're on Jupiter time. Alright. Not Jupiter time, because Jupiter time is slower. Which is the Venus time. And if I say delta t minus tau, then I mean that delta is equal to 1, when t is equal to tau, and 0 and t is not equal to that. And I look at the argument of the function operator, and I set it equal to 0. So t minus tau is equal to 0, therefore t is equal to tau. That's how I find this. Alright? And the net result is if delta is this, t equals 0, then delta t minus tau is going to be equal to this tau. 0, t equals tau, and t. And t. Okay. And that's also. So, if we apply this to a system, to G for example, then if I have G of t at a certain time, okay, that G of t is going to be equal to G of t minus tau at a later time. No matter how late that time is. Okay? The system is not going to change. So, the other thing is, if I have delta of t going into a system G of t, then the response of the system is given by the system itself. Delta of t combined with G of t is going to be equal to G of t. That's the property of the impulse input. Right? And the way to prove this is by going to the Laplace domain. Delta of S, delta goes to delta, G of S, and Y of S has to be equal to delta of S times G of S. Alright, so therefore, if the output is equal to the system itself, which means that if Y of S is equal to G of S, then what do I need to have? What does that imply? If this gives me that, then what do I have? Delta of S is equal to 1. Which you know, right? Because you had done the Laplace transform of basic sequence. Remember that? Does anybody know what I'm talking about? Does anybody not know what I'm talking about? Does anybody not know why the Laplace transform of delta is 1? Does anybody not know? You don't know, you don't know, you don't know why that is? You haven't done your homework. It's still confuses you. Alright, let's do it then. The definition of Laplace transform of any function is the integral from 0 to infinity. Actually, it's minus infinity to plus infinity, but we don't deal with systems that start before time equals 0, right? We just eliminate that. We start the clock, that's time equals 0. Before that, I don't care. If there's an initial condition, right, then means that there was a force acting on the system beforehand, but I don't care about that. I only take the initial condition. Remember that. Oh. All initial conditions mean that there was a force acting on the system before I started. So the definition of it is x of t multiplied with e to the minus st dt. Everybody know that? Hopefully. So if x of t is delta of t, that's the Laplace transform I'm looking for, then I replace this with delta of t e to the minus st dt. Okay? And then from 0 to infinity. Okay? So what does that mean? Delta of t is only valid at time equals 0. Right? It's 1. Everywhere else, it collapses to 0. Right? So I really don't need all that interval from 0 to infinity because it's 0. All I need is when time equals 0, and that's 1. Okay? So I put 1 in here, which means that I'm implying that time is equal to 0. Okay? Otherwise it would be 0. Got it. So if time is equal to 0, this becomes e to the minus s0, which is what? 1. And the whole integral is disappeared because I don't need all the time. So all I have is 1. There's no integral anymore, so therefore this is equal to 1. Okay? That is the Laplace transform of delta of t. It follows immediately by the definition of delta. Alright? Delta does two things. One, it reduces this to 1, and it collapses the integral. So I don't have integral anymore. If I had still the integral, alright, then the integral of 1 et would be t. But I don't have the integral anymore. Okay, why? Because I'm only interested in that point, not the rest of the t goes to infinity part. Because it's 0. Make sense now? Does it make sense? Anyone not understand? Well, that's very important, guys. It's extremely important. You have to not memorize that the Laplace transform of delta is 1, but understand why it is so. Okay? And in order to understand that, you have to understand the definition of delta, which is a purely imaginary thing, not complex, but in our imagination. So we use it at our heart's content, as long as we do mathematics. When we do physics, we cannot use it. Okay? Alright, so now what we have said is the if I give delta of t to any system g of t, what I get is y of t output equal to g of t. Alright? In order to identify a system, what a system is, all I have to do is give it an impulse. And look at the output. The output is going to be the system. Okay? Alright? Yes?
Does this mean that, for example, in the spring dynamic system, if you give one external, you will see the behavior of the system?
Right. When you have the string damper system, exactly that's the first example. Alright. The system is, what is the system? E to the minus at, the response, x0 minus f external divided by k, plus f external divided by k. Alright. The system itself is this. Everything else is outside of the system, f external. This is my system. Okay? My system g of t is e to the minus at. That's all that I need to know about the system. Okay? And if I give 1 to this, then I'm going to get e to the minus at. Okay? What does e to the minus at look like if it were a signal? What would it be looking like? Like an exponential decay, right? To 0. That's a signal. But it's also representation of the system. Okay? Because the signal and the system are the same thing. The only difference between a signal and a system is what? What? Memory of the system. The system needs initial conditions and all other input after that. The signal doesn't care. The signal, this is a signal. Time up. Alright. E to the minus t from 0 to infinity. Okay? So that means that you have minus 1 over s times e to the minus s infinity minus e to the minus s, 0. Okay, and that is 0. And this is 1. So what we have is minus 1 over s times minus 1, and this is 1 over s. Okay, where was that question? So if the integral doesn't collapse, just like it did for delta, then we have to take the whole integral. Okay? And if you apply the same technique for all the other functions, all you have to do is take that integral. And that integral, if there is a complicated function like cosine, for example, then you have to go into UV integral. And I highly recommend you're not going to need to calculate the Laplace transform of the functions in your life. There are tables for them. Okay? But it's highly recommended that you exercise yourselves into finding out the Laplace transform of many different functions. Particularly the cosine and the sine and the exponential, the basic signals that we talk about, the ramp and stuff, or the derivative. Okay, you have to find a secondary because that's important for us transforms. That you not only have to remember to check in the table, but you have to do yourselves if you want to distinguish yourselves from a technician as an engineer. Okay, if you want to underline that. So what we have said is linear time invariant. For the linear part, we have superposition and scalability, and the time invariant part, we have the time shift part. Alright? So, if I, for example, consider a input, any input, alright, any arbitrary input, not a formal basic input like the data or the unit step or any arbitrary input, u of t. Okay, and let's say that it goes like this. We don't consider this one, so I'm going to start from t equals 0, all the way to t equals whatever. Okay? Now, if I take this u of t and multiply with delta of t, okay, what happens is delta of t is going to be 1 at t equals 0 and 0 everywhere else. So we're going to have 1 here, okay? We're going to have u of 0, and everywhere else is going to be 0, so when I multiply it with that, it's going to collapse. Okay? If you don't follow, stop me, alright? I want you to understand this. So what I have is for this function, the following. 1 here, and u of 0 here. So I have u of 0, a single point. Okay? Alright? That is u times delta. Everything else turns into 0. Now let me add another delta t to this. Okay? Let me have u of t, okay, times delta t minus tau. Then the delta is going to fire up at tau. T equals tau. Okay? Everywhere else it's going to be 0. So this part is collapsed down to 0. This part is collapsed down to 0. I have a 1 here with u with delta of t, and I have u of tau here. Right? So whatever I do with this, okay, it's going to give me the value of the function at that point. Right? Multiplied by 1. So what the delta does is collapses the input anywhere where it fires. Okay? And that point, ladies and gentlemen, is not a function anymore. It is a constant, u of tau. Okay? And if I take delta of t and combine it with g of t to get y of t. Okay? If I do delta t times u of t and combine it with this g of t, then what I'm going to get is g of t. So this is going to be g of t. Okay? I'm only considering the t equals 0 part. So what I'm going to have here is g of 0, okay, times u of 0. Make sense? Because the only point where I observe my system, this is the system now, not a signal. It could be a signal, but now I'm considering that it's a system. The only thing I'm considering is this. Everywhere else, it has collapsed. Both the system and the time. Okay? So all I'm doing is multiplying that g of t with this thing, with this constant. Right? So what I have here is, if I have delta of t times a, for example, since this is a scalable system, okay, what I would have is a times y of t, which would be a times g of t. You understand that, right? Scalability is what is this. If I scale the input, then I scale the output, no matter what my g is. And my g is linear and time invariant. That's the only condition that I must have. Make sense? Who didn't understand this?
I just have a question. The first one, how getting delta into the g of t makes the output g of t. Shouldn't it be
Okay.
delta of t?
Let's repeat this. Then, if I have delta of t here, then I'm going to have g of t, right?
No,
Because-
this is the point they don't.
What?
No, this is the point they don't understand.
This point?
Yes.
Okay.
Is it-
Go to the
should it be
Laplace
better?
transform, like we remember here. If I give delta of t to g of t, I'm going to have y of t. I don't know what y of t is going to be, the output. So I go to the Laplace transform. So, and this is the convolution integral of it. Alright, I don't know what that's going to be. I'm calculating that. So instead of doing this, which is integral, I go to the Laplace domain, which is multiplication. So I go delta of s, g of s, and y of s. Now I know in the Laplace domain that this is going to be equal to delta of s times g of s. Right? Because that's the beauty of Laplace domain. And I also know that this is equal to 1. So y of s is going to be equal to the system itself. Okay? Now here you understand, the system is the output. This is the signal, this is the system. So there is no difference between representation of the signal and the system. Okay, other than the memory that the system requires. Alright? So I can call a signal a decaying or oscillating signal. Okay? And I can represent a system, second order system, just like that. Right? So, actually, if I take a second order system and I give it an impulse input, okay, an impulse input, 1, okay, then this is what I'm going to see, the output. And that is the system. Okay? So the signal represents the system. Okay? Make sense? That's important conceptual. Very, very important. So do not confuse systems and signals and think that they are different things. The only difference is that the system has memory. It remembers, like a woman, what you have done to it in the past. Never forgets. Alright? 10 years ago you did this. Yeah. So boys, remember that. Women, your wives, future wives are going to be sisters. Alright? Whatever you input them in the past, it's going to come to you 10 years later. So, you understand that? No? Alright. If I multiply this one with A, what's going to be my output? A. Okay? Well, that A is, for example, U of 0. A constant. Okay? That here I'm going to M of 0 times G of T. Okay? Because the system is scalable, this being scalable. Alright. The trick to this is when I do the time shift. Okay? When I do the time shift, I'm going to have U of T times G of T minus tau. Okay? That is going to go into the system. Now this is going to turn into U of tau. So U of tau minus T minus tau. Right? And the system, sorry, I have to shift the input. So that is going to stay, and the system is going to be G of tau. Okay? Because that's the only point tau in here that I'm looking at the system. Right? Everything else has collapsed because I multiplied it with the delta. Okay? Now I'm going to do U of T minus 2 tau, G of T. I'm going to shift my thing from tau to 2 tau. Okay? Now my output is going to be 0 and then 2 tau. 2 tau times U of T minus tau. Okay? You have empty loops. Some of them have empty loops on their faces. Who doesn't understand this? You remember, there's no problem with not understanding. The shift. Cheetah. That's it. Alright, I'll repeat it here. We have U, okay, input, and tau here. So delta T minus tau times U of T, this being U of T, and this being delta at T equals tau. You understand that? Hopefully, alright. Then all I have is everything else being 0. All I have is this constant number, which is U of tau, okay, times 1. So I have U of tau. Okay? That's going to, if I put this T minus tau times U of T, only this constant into the system, at T equals tau, I'm going to have G of tau, right? You don't understand that? Okay, let's say I have G of T. Okay? I'm going to multiply this with G of T now. Okay? Because I'm multiplying G of T, okay, with U of, I forgot the delta, u of t times delta t minus tau times g of t. Okay? Now this is u of tau. Okay? You understand that? U of tau. Right? Now that is going to give me u of tau or t minus tau. Okay? U of t minus tau. Same thing. Times g of t. But the system is invariant. So g of t at any t, okay, is equal to g of t minus tau. Right? That's the same thing for the system. So I continue like this. U of t times delta of t minus n tau. I do it here, here, here. Okay, what I do is I'm giving the system one input, delta t, and I get g of t. Now I'm giving the system another input, delta of t minus tau. Okay? Then I'm getting g of t minus tau. Now I'm giving the system another input, u of t times delta t minus tau. Then I'm getting this being a constant, u of t minus tau times g of t minus tau. But this is equal to g of tau because the system is invariant. Right? The system is scalable and the system is time invariant. I can both multiply the input and get the output multiplied by a same constant, and then I can give the system an input anytime, and I can give the same input to the same system at a later time. I take the same output. Okay? Is that tough to understand, or do I make it tough to understand? But anyway, the bottom line is, you add all these things up. Why? Because if you give a system an input A, alright, and you get the response B, okay, then if you give the system an input C, then you get the response D. If the system is linear, then it's superposable. Then A plus C as an input has to give you B plus D. That's superposition. Okay? If this is an output, and this is an output of the system, so this input and that input, then this plus that is going to give you this output. Superposable. Okay? You superpose the input and you superpose the output. Remember the example that we gave? If f of x is equal to 3x, alright, then say x equals 2, then the response is 3 times 2, 6. If the x is 4, then the response is going to be 3 times 4, alright, which is going to be 12. Now this is an input, that is an input. If I add the 2 plus 4 as an input to this function, then I have to get 6 plus 1, 18. Do I get that? 8 times what? Where is it? Where am I? 6.
The last year.
Okay.
Left for
Alright. So it's going to be 18. Okay? So you add the inputs, you add the outputs. Just like that. If the system is linear, it's superposable. Okay? So I can add all these inputs one by one. Then I can add all the outputs one by one. Okay? The total, the sum of these inputs has to give me the sum of these outputs. Because the system is superposable. Because it's linear. So what I have here is the summation of u of t times delta n equals 0 to infinity. So what I have done here is summation of all these deltas. Well, the summation of these deltas means when n equals 0, n equals 0, I have u of t times delta of t minus 0, okay? Which is this 1 times this u of 0. Okay? Then I have u of t times delta t minus 1 times, which is this 1 times whatever the function is, u of 1. Okay? And then I have u of t plus delta t of 2 tau, and so on. Okay, I add all these together. All these together, these deltas, that are collapsing the system one by one. So I get this, I get that, I get this, I get that. Wherever the system goes, right, I get those values. Okay, if I add all these deltas one by one, acting on the input. Okay. So what I'm doing actually is, if I add them all up, I am discretizing the system. Okay. What I'm doing is, I am sampling the system at this point, I'm sampling the system at that point, this point, and everything. At intervals of tau. The same thing as discretizing the system. Okay. Follow that. Good. So, this is going to give me a rough approximation of the input. Okay? I'm going to have this much error, I'm going to have that much error, I'm going to have this much error. It's going to be a rough approximation of u of t. Okay? But, if I take tau to 0 at the limit, then I'm going to have the exact same input, because I will have sampled the system at 0 intervals. Which is not possible, but it is possible where? In continuous, in infinitesimal. So, if I turn this summation into an integral, so if I say integral of 0 to infinity, okay, u of t times delta t minus n tau d tau, then I will have u of t itself. Okay? So, by superposition, relying on the superposition property of the system, I first do the summation, which means discretization of the input. And then I take that summation to the limit, turn it into an integral, and get the exact input. Okay? So, on the other hand, what I have as the output is these. So, the summation u of t minus tau, g of tau, okay? Sum all of them up. I get almost the one. Okay? But if I take this integral now, okay, g of tau times u of t minus tau d tau, I'm going to get the exact one. Okay? So this is what we call the convolution integral now. Which means that if I have u of t going into g of t, having y of t as the output, y of t is given by the convolution integral, which is u of t involved with y of t. Okay? And that's going to equal to integral 0 to infinity g of tau, the system, times u of t minus tau d tau. Okay? Now that's going to give us the real definition of the system, if you notice. Because we're talking about the input into the system, input into the system at every single point of time. That's what it is. You already understand. Okay? That's what it means. I am taking into account the effect of all these single inputs, okay, that make up the continuous input throughout the existence of the system. The existence of the system. Make sense? That's why we're saying that the system has memory, because it's integrating the effect of all these inputs in time. Okay? That's why we say like convolution means like u of t going through g of t. Okay? All time. From time, beginning of time to infinity. Okay, g of t, u of t going through. İçinden geçiyor. Neye geçiyor mesela? U of t is Fenerbahçe, and this is Glasgow Rangers. Tonight, we're going to convert Fenerbahçe with Glasgow Rangers. Okay? So what's going to happen? Fenerbahçe is going to go through Glasgow Rangers. Okay? Alright? Now, burada Galatasaray yok. Olmasın. Kimse kalırsın. Kim Galatasaraylı burada sarılma. Galatasaraylı var mı? Yok, çok güzel bir Kim Fenerli? Şöyle bak. Çeksene. Neyse, vazife yapacağım. Okay. So, this is the convolution integral, ladies and gentlemen, and you can convolve any signal with any system through this integral. Just like the Laplace transform, it's going to be difficult sometimes, okay? And this is, remember, tau and tau, okay? So here, t is my real variable, okay? I'm looking at the response of the system at my real time, alright? And tau is just a dummy variable that I use inside the integral, and inside the integral, tau is going to disappear. Okay, so I'm going to be left with real time. Alright? Yeah.
How does convolution relate to memory? I didn't understand.
Okay, that's fine. Did you understand this? Yes. Because the system is superposable, I am evaluating every single input, which is what I'm showing through here, every single input separately on the system, and I'm measuring the outputs. Okay? So, just like I did here, I'm adding all the inputs. Okay? So I'm saying f of x1 plus x2, right, gotta be equal to, okay, or f of x1 plus f of x2 has to be equal to f of x1 plus x2. Okay? This is x1, this is x2, and this is f of x1, this is f of x2, and down the line. So what you want to say is g of x is a system, okay, that takes x and turns it into 3x. Alright? So the system input x1, 3x1, x2 goes into 3x2. Okay, up. So, yeah. Okay, so x1 plus x2 go into the system, and what I get is 3x1 plus x2. Okay? Alright, so I do the same thing here. x1 plus x2 plus x3 plus x4. Sum them up, integrate them, you get u. You understand that? Because what we're doing here is, imagine that this is a comb, okay? And what I'm doing is I'm combing the function input with a data comb. Okay, I'm going through the function. Okay, like a paper shred. And then I'm going to put all the shreds here. Okay, but I take this one. This is this whole paper. I shredded it into these pieces. Okay. I put every piece in the system. Whatever that system is. For example, the copier. Okay. I took the copies of every single sheet. And then I add them up and integrate them. I have the whole sheet. Okay? And I add these, and I integrate that. I have the whole copy of the sheet. Okay? Integrating means adding them up, so putting them side by side. Okay? So,
Memory is the x1, x2, x.
memory is inputs. This input.
System calculates.
I have taken this input. Alright, you gave me this. Alright? You treated me like shit on November the 6th, 2008. Okay? And then on September 12th, 2009, alright, you cheated on me. Okay? And then you didn't bring me a flower on my birthday. All these inputs are registered. Okay? In the memory of the book, the system. So this is what you get. What is that? A huge, big pile of shit. Okay? If you give shit, you get shit. That's what we call shit in, shit out. A SISO system. Okay? Actually, in controlling the single input, single output system, but it's shit in, shit out. What time is it? You can do it. Yeah. Okay? So you can learn this shit. Okay? So this is the convolution integral. And that, okay, tau, look, remember now, I'm changing tau from 0 to infinity on infinitesimal increments. Okay? So I'm taking into account the effect of one value of tau, the next value of tau, the next value of tau, the next, adding them all together. Okay? So I'm passing every single input through the system. Okay? Now you can say that n equals 0 is a function. Okay? N equals 1 is equal. Alright, then square. Then charge, whatever. Every single one is going to pass through Glasgow region. The defense, midfield, forwards, everyone are going to pass through. We can imagine the score. And of course, who is the integrator now? Mourinho. Jose Mourinho is the big integrator. Alright, so we have the convolution integral now in our pockets, I hope. Okay, but of course you need to go home and study like hours and hours on this until you do all this by yourself without looking at any source. Okay, any archive. So now what we're gonna do is we're gonna do the same thing on a discrete system. And this time, u of t is going to become u of n, g of t is going to become g of n, and y of t is going to become y of n. Convolution integral u of n convolved with y of g of u of t, g of n, okay, is going to be equal to the sum from n equals 0 to n. have tau anymore. The n equals, that is n tau, as you remember, g of n. I'm sorry, now. Remember, this is t. I know, we just talked about it. I'm kidding. Alright, u of t, g of t, real time is here. This is the dummy index. This is my real time index, so my dummy index is going to be n. Okay, or l, or k, whatever. So, g of n, u of n minus n, d not dn. Okay? So now what we're going to have is the summation of this and that. M changing and staying the same. Okay? One really important thing in the last 10 minutes I can tell you is the following. A system could be, for example, any representation looking at a signal. It could be this. That could be your system. Just like this could be your signal. How do you do that? For example, this is u of t, okay? And then you have to collapse it afterwards. But not collapse it before, so you have to multiply it by some form of a one-way form of the delta function, right? So you have to figure out the mathematics to do that. So we can do it, all right? So this is, let's say this is your system, G of t. Just like it could be any signal, it could be any system. This could be your system. Okay? In discrete time, your system is going to be looking like this. Right? You're going to have, for example, this is x0. Let's say this is x1. Alright? Then this is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, all the way to n. Okay? And let's say this is your g of n. Just like in a g of t. Here your g of t would be x0 times b to the minus whatever tau is, t over tau. Okay? Here, your system is going to be g of n is equal to 0, 0, 0, and that's when you start here. N equals 0. And then you put the next point, 1 over 2. And then you put the next point, 1 over 4. And then you put the next point, 1 over 8. So on and so forth. Alright? This is going to be your system. Your system could be this. Alright?
Sir, the second one, why wasn't the convolution?
Which one? This?
Yes. We changed the interpretation.
Well, because I'm time domain. In time domain, either continuous or discrete, I need to convolve. Okay? Just like in here. All I have to do is change everything here from t to delta n. Delta n minus n. Okay?
So only in the Z, we changed the interpretation.
Only in the
Z.
z.
In the beginning, we still the Z transform, and we changed
The z transform
Yes.
and the s transform, they are the same thing. Transforming from time domain to the frequency domain. Right? Totally different. Frequency is 1 over s. So in the frequency domain, your time is standing on its head. You don't know what's going on there. You can only imagine. Right? It's like a 15th dimension. You can imagine it in math, but it doesn't exist in reality. Right? So The mind is an infinite resource. Actually, use it as much as you can for the imagination. So a system like this, at n equals minus 1, 0, 1, 2, 3, and 4, okay, you have your g of n is going to be equal to minus 1, 0, 1, 1, 1, 0, 0. You have to put these zeros in because that belongs to the system. Okay? Even though the rest also going to be 0, but these are infinite. So they are part of your system. Okay? And this is also part of your system. So you have to add that. If it's indicated, you add it. It's just like your thing here started from here. E equals minus 1. Minus 1 second. Right? Where you start time is totally up to you. For convenience, we start time at 0. But sometimes it's necessary to start time at an earlier period. Okay? If the system is sensitive to some past inputs, then we do that. But whatever we do, we indicate time equals 0 with an index or with a continuous variable. Okay? So with the continuous variable. Okay? With x at time equals 0 is x 0. This is equivalent to that. This here is n equals 0. Okay? Follow me? Right. I know I'm throwing a lot of concepts too, but once we start using all these terms, it's going to be sounding familiar to you all. Alright, now here we have something interesting right here. Okay? What we have is a time shift operation, as you see. Alright? Now, if I consider, for example, this in a different way, I would write it like u of minus m minus n. Okay, that would be equivalent expression to this. Alright? But that minus sign here has a very deep significance in how the system or the signal looks. For example, let's say my system is this. Alright? So I have that configuration of the system. What would be the representation of g of minus n? That would be a question that I would ask you in the exam, for example. If you change the sign of this index, what would it be? Now we know that g of minus 1 okay, is minus 1. And is equal to minus 1 here, 0 here, 1 here, 2 here, 3 here, 4 here, and 5 here. Okay. So what would be the g of n of minus 1? G of minus n of minus 1. Here then, this would be g of minus 1 turns into plus 1. Okay? If I switch to this from that, all the n's are going to have the opposite sign. Okay? So g of n is going to turn into g of minus n. Okay? If I wanted to do that operation on the system, reverse the sign. Okay? Not that I'm going to do it every time, but if I did, then minus 1 would turn into g of minus 1 would turn into g of 1. G of minus 2 would turn into g of 2. Okay? G of 4 would turn into g of minus 4. Okay? Only g of 0 would stay g of 0. Okay? If I want to switch the sign of the index, that will happen. Now I know that g of, let's say, minus 1 1. But now I'm looking into g of 1. And what is that? 1. So my g of minus 1 is going to turn into 1. Okay? Minus 1 is going to turn into this. G of minus 2 is going to turn into G of 2. Right? G of minus 3 is going to turn into 0. G of minus 4 is going to turn into 0. Okay? Minus 3, minus 1. Now G of minus 1 is going to turn into G of, G of minus 1 is going to turn into G of 1, so that's going to be 0. And then it's going to be nothing anymore. So look what I have done to the signal. I have taken this and swapped it across to the y-axis. You see that? I changed the orientation of the whole signal. Okay? But if I did, for example, the following operation, I have G of n here. If I wanted to look at minus G of n, okay, then G of 1, which is G of minus 1, okay, which is minus 1. G of minus 1 is G of minus 1 is minus 1. What did I do? This is not the function of that. Nobody tells me that I made a mistake. Alright, so wait 2 more minutes, I'm going to correct myself. Let's see. Tell me what G of n is. What is G of n? No, here. Minus 1, 0, 1, 1, 1, 0, 0, right? Minus 1, 0. So, what is this represented as? Here is n equals 0. So, here I have 0. At minus 1, I have minus 1. N equals minus 1. At n equals 1, I have 1. N equals 2, I have 1. N equals 3, I have 1. N equals 0, 1, 2, 3, 4, 4, I have 0, and 0. Okay, this is 0. Now I'm trying to get G of minus n. And that would look like the total opposite of this. So G of 1 would be minus 1. G of 0 stays 0. These are 1, 1, 1, and then 0, 0. Alright, so this is minus 1, these are 1. Okay, here n is equal to 1, n equal to 0, minus 1, minus 2, minus 3, minus 4, minus 5. Here n of 1 was equal to 1. Here n of minus 1 is equal to minus 1. Alright, the whole index has changed. N of 2 was equal to 1. Now n of minus 2 is equal to 1. So I switched it across to y. Okay? But if I wanted to do let's put it here, minus G of n. Okay? So now G of n being minus 1 here, okay, minus 1 is going to be 1. Because I'm looking at minus G of 1. I'm going to change now the sign of this. Okay? Not the place of that, but the sign of this. Okay? So everything is going to be reversed across the x-axis. Oops. Okay, so changing the sign inside the bracket rotates the system across the y-axis, changing the sign across the outside the bracket, rotates it across the x-axis. Okay? Signal manipulations, ladies and gentlemen. These are extremely important stuff that are going to play a very big role in our calculation of this. Okay? Let's take a break. What I'm saying of the integral. So this is actually u of minus m minus n. We prefer to write the index of the summation or the time, the integral, first. Okay? So what that says is that we have to reverse the input. We have to leave the system as it is. Okay, so if you want to combine, for example, a system, any system, G of n, with any input what we have to do first is write that down. 0, 1, minus 1, 2 as G of n. And then reverse the U of n. 1, 1, minus 1, minus 1. Okay? And then I am leaving the time as it is, n, alright? I am moving on n, but time is what I'm shifting this with. Okay, so what I'm going to do is u of minus n here. Okay? I'm going to take first n equals 0. And do this multiplication first. Get y of 0. Okay? So the multiplication is going to give me this corresponding is 0. Corresponding value is 0. Corresponding value of g is 0. Okay? The corresponding value here is 0, 0, and 0. Okay? So, whatever the summation tells me for n equals 0, I'm going to say g of 0 times u of 0 minus, I'm going to start n from here. I have not from 0, see that's one example, minus 2. Okay? That's one example of why we want to start time before time equals 0. So, g of 0, u of 0 minus the first value of n, minus 2. Right? That's for n equals minus 2. This whole thing. Then I'm going to add to it the next in the inside the summation, which is going to be n equals minus 1. So all the values that I have for n, I'm going to put minus 1 in. N is going to stay the same. G of 0 and u of. Now, this is u of minus, alright, so minus n equals minus 2. minus 2 minus 0. So u of minus 1 minus 0. Okay? This is going to give me g of 0 or n. This is n. Follow me? So I'm just following the recipe that I see here. And then I'm going to continue with n equals 0. And then n equals 1. Okay, n equals 2, n equals 3. All the way down to I have 0, 0, 0, 0. So then I'm going to be done. Okay, so I'm going to do all these, and I'm going to add these values up. Okay, g of 0 is what? 0. U of minus 2, which means 2. Okay, g of 2 is 0. Okay, so it goes on like that. So for each one of these, I'm going to get a number, a scalar. I'm going to add all these scalars up, and I'm going to get this scalar. And that's going to be the value of y of 0. Okay? And then what I'm going to do is I'm going to move m by 1. So I'm going to have m of minus 1. So I'm going to have g of 0, g of n here again. 0, 0, 0, 0, 1, minus 1, and 2. Okay? And then I'm going to time shift my n by 1. So it's going to be u of minus n minus 1. Okay? So that means that I'm going to move this over by 1. What I'm doing here is I'm multiplying this with that, this with this, this with that, this with that, this with that, this with that, this with that. Alright? So I'm going to have 0, 0, 0 times 1 is 0. 1 times 0, 0, 0, 0, 0. So n y of 0 is going to be 0. All the multiplications are going to give me 0. Okay, because zeros come across each other. So now I'm going to shift this by 1. So this is n equals minus 1, minus 2, minus 3. Okay? Minus 1, minus 2, minus 3. This is minus 1, minus 2, minus 3. Okay? So now this is going to go to minus 2. So minus 3 is going to be 0. Minus 2 is going to be minus 1. Minus 1. 0. This came here. This is going to be down here. These two are going to shift by 1. This is going to shift by 1 over here. And then I'm going to have this 0 coming here, and this 0, 0, 0. Okay, so this is shifted by 1. Alright?
About the minus
Right, that's what takes care of this term. That switch. My u is actually this. That minus 1, alright, turn this into that. Now I'm taking this switch over, shifting it by 1. Then I'm going to shift it by 2, shift it by 3. Okay? Then I'm going to multiply all of these again. This times this, this times that, this times this. Now here, I'm going to have a non-zero value. Here I'm going to have a non-zero value. Here I'm going to have 0. Here I'm going to have 0 and 0 for all. Okay, so here I'm going to get 1. Here, no, the only thing I have is 1. So all these other sums, 0 plus 0 plus 0 plus 0 plus 0, blah, blah, blah. So y of 1 is going to be 1. Okay? Now, I'm not going to do all of this, but there's an example in my slides, okay, that I did both geometrically, like this, and also algebraically like that. So I want you to study that example. Right? Learn it real well, and then try to do it without looking at the notes. Right? See if you can get the right result. Learn the trick. So first, you take G, and then you switch over the y axis the input. Right? And then you take the G, the system, you take the switch over and shift it by 1. Just like this time. Okay? And then multiply that, just like this says, and then this time, so you don't iterate over n, you iterate over m. Okay? You increment m one by one. And then you do the cross multiplications. And then you do that. Now, this is one way, this is the addition, summation way. This is geometric. Right? And then there is one also, the tabular form, in which you put u here, and then g here. Okay? What is my g? What is my g? Here, 0, 1, minus 1, 2. So you say 0, 1, minus 1, 2. Okay? And you put u here, on top you put the u, this, and that, and then you switch it over, so you have minus 1, I think you switched it, I can't remember now, but anyway, it shows on the exercise sheet how you're going to do the tabular form. And here what you do is, once you put u here, which is going to be, I guess, minus 1, minus 1, 1, and 1. So you start from here, go backwards, because you have to switch it. Okay? Wait, at 0, it has to be plus 1. At minus 1, it has to be 1. And then at minus 2, it has to be minus 1, minus 1. So, and then you do the multiplication like that. It shows on the exercise sheet how exactly you do it, right? With all the manipulations and everything indicated. So I'm not going to spend time on it, but any two signals, or any system with a signal, or any two systems, you can combine. Because a sine is a system, if you look at it mathematically. Okay? So that's going to be your homework. Alright? Do that in your homework for this week. Study that real well. Alright? Yes?
What does this give us?
What?
What does this give us?
Say it again.
What does this give us when we combo two systems?
What?
What do we get from this?
The output
Yes.
of the input going into the system. Y of n. You're going to get u of n going into g of n. You're going to get y of n. Right? So you're going to say y of 0 is 0. Right? So you're going to have y of n is 0, 1, 1. Okay, that's your output.
So output will be a constant.
Every value of the output at each time index is a constant. So you're going to get a constant, a scale. You're going to get the value of the output signal at that time index. Okay? Like, for example, when you give a delta of t to a system, g of t, you get y of t. Let's say this is delta of n, g of n, and y of n. Okay? Now, let's say delta of n, as you know, is 1, 0, 0, 0, 0, 0, and n equals 0, this is 1. N equals 1, this is 0. Remember? That's the delta signal. Okay? And imagine that your g of n is, for example, minus 1, 0, minus 2, 4. That's your g. Okay? So the output is going to be the system, because you're convolving it with the delta. And the output of delta input is the system itself. So your y of n is going to be g of n. Okay? That's going to be your y of n signal.
So we shift the delta function to find all the
Well, whatever you do, okay, on the integral, on the summation, you apply it to the input. If this is the input, you do what the recipe says. Alright? So learn what the recipe says, and learn how to do it with your eyes closed. Okay? It's very simple actually. Once you understand that, the formula requires you to shift, multiply, and then sum. Okay? Shift, multiply, and then sum. Okay? All the output to get one scalar for each n. Alright? That's going to be your output at time n. Alright? Is that clear? Once you do the example, okay, and trust me, you need to do the example, then you're going to be able to do anything in the example. What we're going to ask you, for example, is, let's say, the convolution of e to the minus at with e to the minus bt. Okay? A and B being A arbitrary scalars. So, there is one e to the at signal or function, I don't care. You're going to convolve it with another, maybe a slower system, e to the bt. Okay? This will be the time constant is going to be 1 over A. Time constant is going to be 1 over B here. You're going to convolve this and that. Okay? You're going to learn how to do that for any arbitrary signal, any arbitrary system. And now the same thing you have to do with a discrete system. Convolve this with a slower system. Okay? A signal with a system. A system with a system. Signal with a signal. Doesn't make any difference. Alright? So learn that. Very important. Now, having said all this, we can go into the discrete system analysis. What we have done with the continuous systems is first, we represented them with a force balance. For example, what did we say? Ex dot plus kx equals k external. This was the force of the damper plus the force of the spring equals F external. Okay? First you do this. Then you turn this into a differential equation. Okay? Then you solve the differential equation subject to x0, for example. Right? You solve the differential equation, which is what? X general of t is equal to x0 minus k. External divided by k e to the minus k over dt plus x external divided by k. Okay? And then we show this as a the system. G of T coming out X of T. What? This system here has a toll in it, which is that. So we indicated it as a feedback, negative feedback diagram. Remember that? F divided by B goes into and subtracted by X dot. Okay? Where did that come from? Came from this. If I leave X dot alone, then I get minus K over B, X plus F over B, right? If I leave this alone, X dot. So F over B, okay, and K over B, X. Now, if this goes in there, I put a integral here, I get X, and I multiply X with the pole, K over B, and I put it as a negative, add it to F over B, I get X dot. Alright? Child's play. Nothing to it. Okay? And then I did the same thing in the S domain. F of S divided by B going into, now this is going to be X of S times S. Remember X dot. The Laplace transform is X times X of S. Now I'm going to integrate it to get X of S. So if I get X of S into the system and get out X of S, what is the system? 1 over S. So integral is 1 over S. Integration is time in time domain means division by S in the S domain. Okay? And I take this, multiply it with K over B, and I supply it in here. Okay? Now I can do this 7, yes? Right? As an algebraic form. What does that say? X of S times K over B, alright, with a minus sign, added to F of S divided by B is going to give me X of S. I'm going to multiply all this by 1 over S. I'm going to get X of S. Right? The block diagram, the information, global information is giving me what's going on here. It says, take X, multiply it by K over B, subtract it from this, okay, divide everything by S, that's equal to X of S. Okay? That's the block diagram, the video. So now I can manipulate this because I have no integral or anything like that. It's all algebraic, multiplication and division. So, minus K over B, X of S, plus F of S divided by B is equal to S times X of S, which is what that is, the same. Okay? So, I move this over there, plus K over B, X of S. This is removed from here. And then I take X of S in parentheses. What have I left? S plus K over B. Okay? Now I want to find X of S. So I divide everything by this. F of S divided by B divided by S plus K over B is equal to X of S. Okay? Now then, this X of S equals, I'm going to write the same thing in a different format. 1 over S plus K over B times F S divided by B. This is my output, and this is my input, right? So, X of S is the output, X of S divided by the input, the input f of s is equal to whatever left in here. 1 over b s plus k over b. Okay? Right? The same thing. All algebra, nothing devious here, nothing difficult. Multiplication, division, subtraction, addition. That's all. Okay? So, what I'm looking at here is f external in the Laplace domain, f external of s going into the system, g of s, giving me x of s. The Laplace domain transform of this. So I'm looking at the input, the output, or the input 1 over b, giving me the output. So this multiplied by that is equal to the output. Right? In time domain, I can't do this. What do I do in time domain? Convolution. Okay, convolution takes an integral. Students hate that. Alright, so what do? You go to the S domain. Laplace, so you have to take Laplace transform everything. But students hate Laplace transform S as well. So what are they going to do? They're going to look on the tables. Okay? But we recommend that you learn how to do the Laplace transform. So, what am I actually doing here? I am doing this. I'm taking an external of x. Okay? I'm multiplying it again, 1 over b, giving it into the system, 1 over s plus k over b, giving me x over s. The exact same thing. Okay? Since it's multiplication, I can take this from here to there anyway. It's multiplication. Multiplication is good. You can change the order. So 1 over b doesn't have to be here, doesn't have to be here, it can be anywhere. Okay? So this is my system. I can write this as 1 over b here. Okay? Give this one. Your answer. Alright, so I call this the transfer function of my system. Why? Because it takes the input, transfers it into the output. Right? The transfer function of the system. I describe my system as this transfer function. So my g of s is equal to 1 over b, s plus k over b. Okay? What I can do is I can multiply everywhere by b to get rid of the 1 over b over there. So b times b equals, that becomes 1. Okay? This b cancels that, b1 goes here. So bs plus k. Okay? Same. All algebra, nothing but. So I can express my system any one of these formats in the continuous format. Okay? Now how about in the discrete format? What we have in the discrete format is a little bit different. Okay? What we're going to have is the following. We're going to have an input. Okay? Then we're going to have the output. See that the forward path, as opposed to this forward path, has no integrator. So something has to be there to do the integration, because all systems are accumulating the height. Remember? You did this, you did that, you did this, you did that. All the inputs have to be accumulated somewhere. We do it on the feedback path. So we put a delay bar. and then we multiply it with the whole of the system, and we add it. Right? The price of taking the integrator on the forward backward path is to turn this into an addition. Okay? So what does the delay box do? The delay box holds this information for one period. Now remember what the computer did. Took this information, held it one period, and then turned into this information. So this is what the hold means. Right? I'm taking this, I'm holding it until the next time. Okay? That's called a zero order hold. Or in math, ZOH, zero order hold. That's what the computer does. This is a digital system, it's a computer. It has to hold something. Okay? So it holds the information. Okay? What does it give? The information that it started to hold before. Okay? This is n. It started to hold this at minus 1. So it gives you y of n minus 1. Okay? It spits out that information because it's been holding it. That's the grudge. Grudge nedir? Kin. Tuttuğu kini hemen söylemiyor. Zaman geçtikten sonra o kadar hain. Okay? Kadın. Dolayısıyla kulak bize ne diyor? Bunu take this, what does the kulak tell us? Take this, multiply with p. So our information output of the function. If your input is the impulse function, then the output is the system itself. The best way to find out the character of a system is to put it under stress. Right? And what is better than delta as a stress? You just give it a punch, 0 time, huge punch, and see what it does. Okay? Kick it in the butt, and then see what it does. If the system says, oh, that's perfect, why did you do that to me? That's first. If the system response is, that person. So to find out about the real character of a smiling face, nice personality, what the person shows you in normal times versus the character, what the person really is. Alright? What do they say to find the character of a person? How can you find it? In the gambling table. When there's a lot of stress to lose money. During travel. And there's a lot of distress. Okay, changing situation all the time. And when you're drinking, when the person is drunk. Right? It's very bad to talk about drinking during Ramadan. Okay, this is my thing. So to find the character, the real system, give it an impulse. Begin the box. Okay? So how much time?
1 minute.
1 minute. 1 minute. That's how it is. Are you recording? This is terrorist, right? And I am who I am. So I say 1 minute. 1 minute. Okay? So I'm going to ask 4 more minutes. We have 4 more minutes? Or do you want to go? Who wants to go? Alright, go ahead. You're going to do this.